So my name is Jay Pinjarkar. I am working as a research engineer at Maritime Research Centre. So mostly I handle the technical related part in the MRC. Whatever the research has been done in the maritime, I try to convert. We try to convert in the more application point of view to make a product service out of it. So today I'm going to present the SRN, that is a shipping related noise, and MSP tool. So coming to the SRN tool. So shipping related noise estimation tool basically divided into two parts. First one is the instantaneous noise mapping, and second is the cumulative noise mapping. Cumulative noise mapping gives the logarithmic sum of the estimated noise generating from the ship for the particular duration of the time. So you can see that on the left hand side, you can see that you can toggle between the AIS layer, that is the automatic identification system, that is the position and location of the ships. Right now, on the top corner, you can see that you can select the range of the time period, and based on that, the logarithmic summation of the noise will be pop up. So this is about the cumulative noise map. Coming to the instantaneous noise mapping. So same feature you can see that on the left hand side, the bathymetry and AIS layer is there. Instantaneous noise mapping gives the real-time calculation of the ships. Is the near real time, because AIS has the lag of around 5 to 6 minutes. So based on that, if we feed the data to this tool, it will give the real time what is the ship. I will just give the demo. On the left hand side, this is the AIS layer, and for the user feasibility, we can on the bathymetry layer. So user will get the complete understanding what is the depth of the ocean at the particular area, because depend on the it is feasible for the user to understand the area of interest, how the environment are there. The vessels, the ships are there, and if we click on some vessels, so what noise it is generating, it will give the result. Okay, so the 47 dB decibels, the noises this ships is producing in this area. So coming to the, I will just give the demo. So after selecting the area, so in this tool we are applied lots of validations and computations for the area selection. So what the right now I have selected the specific area. So according to the area, what is the depth or the in the ocean? So it will give the receiver what is the possible receiver depth we can deploy. So that can be adjusted from the here. So you can see that there are hexagonal patterns over there. So we are considering the virtual receiver point in the ocean that will act as a receiver point over there. Okay, so I will just select the 100 meter depth and start generating the noise. So for each and every index, it will calculate the noise at this particular level. So you can see that right now I run all this backend computation locally. So out of 84 indices, they are continuously calculating. So you can see that this is I selected the area, but you can see that this is very large area. If I selected on this map, so it's looking small, but it is a large area. And for doing the computation for this large area, we initially integrated the only the initial calculation based on the mathematical. But in terms of the computation, it will take more time. For this area, it's taking around 4 to 5 hours. But right now we are implemented the neural network, that is the AI. So the transmission loss calculation is the major factor, how the noise is traveling for the particular area. So I will explain every part. So right now you can see that with the instance we can calculate this kind of result. So I will give the broad understanding how we are calculating, what is the concept behind it. So you can see that the first layer is a data source. So this kind of data we are using. I will go each and every step in the next slides. So first is the data source layer. Then we do the process of cleaning the data, the raw data, and prepare is for the modeling and simulation part. After that, we are applied the modeling simulation part. In that, first one is a source. How the source is generating noise, what level of noise is generating from the ships, and second is how it's propagating through the ocean. So that is the next part. So this both model will be gives the result of the shipping radiated noise and the acoustic propagation model. and both by accumulating both the results, we are getting the noise level of it. So this is the AIS data. AIS data basically divided in two parts: static data, that is the measure the name of the ship, what is the length of the ship, and all those things. And second is the dynamic data. That is continuous change, the location of the ships, the speed of the ship, and the machinery details. So using and the machinery details in this, what is the mass of the engine mass, what is the mounting parameters. So all these factors are fed into the modeling and simulation part to calculate what is the noise generating from the ship. Okay. So both the models are trained based on these parameters of the ships. Right now we are using the latest model, that is a Vatican model. So that will consider all those parameters over there. So you can see that on the below side, these are the vendors for the AIS data and vessel machinery details. This is a private agency that provide the AIS data. So second data source is the environmental parameters, that is mostly available open sourcely. What is the temperature and salinity? Itobo database for the mathematical that will provide the depth of the ocean at every point, and the sediment data. So coming to the methodology of the part, so we use the S3 geospatial indexing for the system that will reduce our computation and as well as the spatial temporal mapping abilities. So you can see when I select the area, the grid that will be using, that is the S3 indices. So what is S3 indices? S3 indices is the system that will divide the globes into the hexagonal patterns at a different resolution. Okay, and each resolution and each S3 indices has a unique identification number. So if I select the area, so the unique identification numbers get sent to the backend, and for each grid that is acting as a receiver point, will be calculating the source and the transmission loss between that. So you can see that I use the lesser resolution S3 indices as a center, that is a receiver point, and to grab the ships around it. Around the 200 kilometers, because after the 200 kilometers, the most of the sound get degraded. So it will use to reduce and capture the ships in the 200 kilometers radius. Coming to the modeling and simulation part, so how we are calculating. So I previously explained that the ship generating for the noise, we are using the Vatican model that will consider the vessel's parameters and all those things. Coming to how this sound is propagating through the ocean. So right now, first one is a sound speed profile estimation. So at a different depth, it will give the different sound speed over there. So sound speed, it depends on the denser is the medium, the more is the sound speed. So we need to prepare the sound speed profile of it and feed this to the PRAM model. PRAM model is a parabolic equation. So you can see that in this side, this is the bathymetry of the ocean, and this is from the source, that is the ship, and this point is a receiver. So this is how the noise is transmitting through this. And I previously demonstrated you can select the receiver's depth. So this is the receiver depth. So according to it, it will give us the 2D mapping of it. So you can, according to stakeholder use, at what level of he wants the data, or he wants to how the noise is there at which depth. So he can easily select in between that. And for this is the receiver point, and this is the ships around it. So between each and every point of the ship and the receiver, we need to calculate the transmission factor. So all this calculation and computations come into the result. For every indices will be calculating the total noise of it. And after the grid has formed, we will doing the interpolation of it. So the spread of how the level will be spread, because between the two receiver points, how the noise will be spread. So we are applying for plotting, we are doing the triangular interpolation over here. So these are some results. You can see that near is the ship. So you can see the darker region is there. The sound is around 120 decimals around there, and the ship is far. It will give the lesser than the noise spectrum over there. This in this result you can see that what level of interpolation we are giving. If this ship is producing less, but the coherence of the both ships gives the more in this region. So that is level of interpolation we are doing over here. You can see that in the heavily traffic area, as I told you, that the transmission loss factor is really hard to compute. Lots of number of transmission loss need to be calculated for such a result. So you can see that for each receiver point, there are thousands of ships around there. For this particular, each receiver has 3,000 ships in the 200 kilometers radius for there. So for this heavy computation, this tool had the capability to develop such a results. You can see that this is the ships are present, but near the coastal regions. So near the coastal regions, the speed of the vessel is less, and due to the sediment factor also. So from the bathymetry, the sounds not get reflected, and all those parameters will be considered. So you can see that the ships are there, but noise level is in a lower spectrum. So that kind of things we are implemented in the SRN2. Coming to the marine special planning tool, marine special planning is a combine for the all stakeholders related to marine and fresh waters. So on the left hand side, you can see that all the planning layers. So at Maritime Research Centre, we work on this, all the spectrum right now, and this tool is in the development phase right now, in the beta phase. So likewise, we are adding continuously the research work in it and adding one by one layer to it. So I will give the some integrated work right now. So you can see that and in this marine special planning, we are not just putting the data, we are computing. Likewise, right now I compute the noise level from the ships. So that kind of computation, we are not directly putting the data and getting the result. We are doing the prediction. The Shlok has presented the API tool. So it's prediction based on the spatial temporal mapping. So that we are also doing. So it's not just data plotting thing. We are doing the scientific calculation in the backend for that. So you can see that we can pop up the multiple layers over here, the major ports in India and all with their details. So this kind of geospatial planning can be do. Coming to the right side of the tool, you can say that for each and every planning layer, you can adjust the necessary feeding parameters to them. So I will just cover one example of the marine spatial planning. This is the application. We are plot the two layers. First one is the noise generating from the ship and the habitat suitability model. So based on the species, this is for the green turtle we are plotted. So you can see that this is the habitat map. This is the potential we are predicted. Lots of green turtles can be found in this region, but lots of shipping traffic is going into this area. So we can plan. This is not. We cannot directly change the route of the vessels, but this can be planned using this tool itself. So you can see that the tool has the capability. If we divert the shipping traffic, so this kind of results can be formed. So such kind of lots of many application can be do from this MSP tool in the future, and I think that the resources of the ocean can be sustainably used using this marine planning toolkit. So that's all from me. Thank you.